So it's a great pleasure to be here. SynTouch was a startup 7 years ago. We're just around the corner at Figueroa and 23rd in the Texera Plaza. I think that's up a little high. And I'm going to talk about tactile sensing and how it can be used in robots. And I'm here a bit under false pretenses, because it's really an opportunity for me to talk to a whole bunch of people here who are in design, because we've realized that one of the things we can do with tactile sensing and some very specialized robots is provide you with an objective sense of what materials feel like. The feel of material is such an important part of consumer products of all sorts. And it was a surprise to us after we started working in this field to realize just how many major corporations were desperate to find something. And I'm hoping I can get some feedback from you. And I brought along our tactile sensor so you can get a sense of what it actually does. And I'll do a little demo of that. So we're interested in tactile sensors, and our original motivation was in fact robotics, both prosthetic hands, which are a form of telerobot, and industrial robots. This is everybody's notion of what robots are like, and it's of course nothing like what robots are really like. They haven't changed much in the 60 years since the Unimate robot was first patented and used at General Motors. They're pretty much mindless machines with hard metal parts that grab stuff and move it very fast, as long as everything is exactly in the right place and has exactly the right mechanical properties that it expects. And anything other than that, and chaos ensues. And one of the reasons is that robots, unlike human workers, have no sense of touch. And people have understood for a very long time, this is a picture from the Norton Simon Gallery, about the sophistication, the importance, the essential nature of touch as one of the ways in which we get to know the world. If you want to make a robot know something about, or a human brain, know something about external objects it has to deal with, there are three major senses that you use. You can use vision, you can use sound, and you can use touch. And if you need vision, it's obvious that everybody's got cheap, very sophisticated video cameras. Hook them up to some software and you have artificial vision. Sound, of course, microphones have been around for over 100 years. If you want the robot to understand touch, what sensor would you use? And that was really the problem. And one of the things we've understood in the 7 or actually 10 years that we've been working on this technology is that it isn't really so much the sensor as it is the mechanical properties of your finger that cause you to have sophisticated abilities to deal with the world, to know what it is, and to handle it. The mechanical properties of the finger, everything from the fingerprints to the soft fleshiness of this and flexibility of the skin to the fingernail, they define what happens when you make contact with something. And you don't get any tactile information until you do initiate a contact. And so the important thing turns out not so much to be the sensory modalities, which of course you have to have, but it has to be the mechanical properties of the finger if you want a sensor to appreciate the world in the same way that a human does. And the exploratory movements that the machine chooses to make, which also define what the sensors will actually get during the collision that's created. So the biological sensors are installed in the skin, and there are thousands of very sophisticated receptors. And we understood from the very beginning that we couldn't put sensors in the skin because skin is constantly worn and damaged. And Mother Nature is clever enough to replace those sensors constantly, and we're not as engineers. So we had to figure out how to get these sensing capabilities into something that is a mechatronic device and keep all of the sensors away from the skin. And so I'm going to show you the technologies that went into this. And you can see the obvious sort of anthropomorphism in the shape here. There's a core structure that has all the electronics where they're protected. It's like a bone. There's the skin, which is clamped down at the top with a plastic thing, which is like a fingernail, also forms an inflation port because we actually inflate the skin, which is a flexible silicon polymer, with salt water, just like what's in your finger. And that turns out to be critical for some of the sensing modalities. In particular, we can sense the deformations of the skin that occur when you collide with something by the changes in the electrical resistance through the conductive solution that we measure using electrodes that are installed on the surface of the bone. We can also pick up vibrations that occur in the skin as you slide over objects using a pressure sensor, which is really a hydrophone, an underwater microphone. And we can pick up the thermal properties by heating the finger the same way that your finger is heated, warmer than ambient objects, and you detect whether things are, say, metal or plastic by whether or not they feel cool or warm to the touch. And that has to do with the heat transfer. And really the best way I can show you how our tactile sensor works is to show you our tactile sensor. So let me just drop out of that for a moment. Or so. Okay. And go to a little demo. So as we say around our lab, ladies and gentlemen, I give you the finger. So here it is, and the first thing I'm going to call your attention to is the colored dots here, which represent the electrodes. This skin is transparent, so some of you at the front may be able to see there are little platinum electrodes on the surface, and that's a map of them, and it's in this orientation. So if I make contact with the finger, you can see a change where I'm poking it. And if I make contact somewhere else, you can see where I'm poking it there, and you can follow where I'm making contact with the finger as I move around in various places. So now I know where I'm touching it, and I would like to know how hard I'm touching it. What you're seeing there in those colors are a graphic representation of the electrical resistance of the electrodes through the salt water between the skin and the core. So there's a wide dynamic range. The lightest touch that I can get here that you can detect is about 30 millinewtons, and about 1,000 times higher is about what it takes for me to saturate this and get up to the red level. So I have a wide dynamic range. But what's more important when I'm handling something is not the force in this direction, which engineers call normal force, it's tangential force. Because if I'm holding something, what I really want to know is how much weight's going to cause it to slip out of my fingers. And so one of the things I teach over at USC in biomedical engineering, I always tell my students, I can't keep you from bringing the world's best crib sheet into class with you when I ask questions. How do you detect tangential force in your fingers? So, well, put your finger down and sort of drag it sideways, and you'll realize that the skin is pulled tight on one side and bulges on the other because it moves, except it's held down by a fingernail. And our skin is going to do the same thing mechanically. So if I set it down here, you'll see where I'm making contact in the middle, and then as I add tangential force swinging back and forth, you see the lateral electrodes, the ones that go up the sides near the fingernail, going up and down in their values. So I can actually extract the amount of force, the location of force, and the direction in which the force is being applied. And that's a fairly essential bit of information for handling objects. Covers essentially what we call light touch. But there's another thing you do. When you go to the store and you want to look at some clothing, first thing you do is you reach out and you stroke it, but you touch it very, very lightly. Not enough to really deform the skin, but enough to tickle the skin. And so we put a pressure sensor in here because when we change the skins, they're easily replaced, they're inexpensive, it takes about 10 minutes. We have to inflate it, and in the upper left, what you see is the pressure. So of course, if I squeeze the finger, you see the pressure go up and down. What's on the upper right is an amplified version of the high frequency of the pressure. And it goes up to about 1 kilohertz, which is really sound, and those are the vibrations that the finger is seeing as it's stroked over surfaces, just the same as your finger would. You touch a surface lightly and you say, oh, that's nice wool, or oh, that's yucky polyester. You're doing that because of these tickly sensations, and you see the vibrations, that you see the high frequencies as I stroke over my wool, and it would be a different pattern if you were able to look at it with enough resolution as I stroke over the cotton of my shirt or over my finger. So that actually gives me very sophisticated ability. It's actually about 100 times more sensitive than your finger in vibration. But one of the things that does make it very sensitive is that it has, you can't see from there, but it has embossed into the surface a pattern of fingerprints. And somewhat to our surprise, when we put those fingerprints into our skins, which takes a lot of work in the mold, the vibrations got about 30 times larger in amplitude. So apparently fingerprints are not just there for the FBI. Mother Nature put them there for some reason, and they actually arise in the higher primates as they started using tools. It's an essential property. And then finally, we have this thermal property. You can look at something and say, I wonder if that's metal or plastic. You put your finger on it. If it's metal, it's going to feel cool. That's because your finger is warmed up. All of our signal processing electronics are in the core. Our finger is about 10 degrees warmer in Celsius than ambient. And we have a thermistor behind electrode 10 near the tip that you would use to tell the temperature of something. And the third one down on the left is the first derivative of temperature, which is the heat flux. So when I make contact with this surface, you'll see a cooling curve. And the shape and duration of that cooling curve allows us, if we control how much force is being applied and where it's being applied, allows us to tell what the thermal properties are of the thing we just touched, just like you can do with your finger. And of course, we can control the exploratory movement because we have all that information about exactly where the contact's being made. And there's some other kind of clever features that Mother Nature designed into fingers that I don't really have time to show you right now, but afterwards I'm happy to let people come up, play with the fingers, see what the signals actually look like, and learn a little bit more about this marvelous machine that Mother Nature has endowed us with. Now the question is, okay, what do we do with it? And let's go back to the slides. Okay, so one of the things you can do with this is come up with better prosthetic hands. Prosthetic hands that are controlled by the muscles, the electrical signals generated by the muscles in the stump have been around for about 50 or 60 years, and they don't work very well. And they particularly don't work well when you have to grip something that might be crushable. And the reason is that if you don't stop it at precisely the right moment, the thing goes from closing to producing very high grip forces and just crushes whatever you contacted. And so the reason, of course, we don't do that with our own hands is that we have tactile sensation and we have reflexes that allow us to stop increasing the force on our muscles when we think we have the right grip. And tactile, you have some idea of how important tactile sensing is, because if your fingers are numb from the cold, it doesn't happen much in Southern California, but I spent 12 years in Canada, so I know about numb fingers. When your fingers are numb from the cold, there's nothing wrong with the muscles that operate your fingers. They're actually up here in your forearm, quite warm. But your hand is essentially useless. The reach into your pocket and pick up something and bring it out of your pocket, you cannot do that at all. And so a prosthetic hand, no matter how sophisticated we make the motors and the linkage and all of that, is going to be about it as limited by how good your hand is when your fingers are numb from the cold, which is pretty close to useless. So we came up with the notion of putting in a very simple version, one of these very simple reflexes that your spinal cord actually does automatically with your brain not even thinking about it. And that led us to a version of the prosthetic hand, which you'll see in this video. Let me see if that'll, there we go. Oh, do we have sound? I guess we don't have sound. Basically what you see here, what I said, this hand has been equipped with tactile sensing. He has no difficulty picking up objects that would otherwise be crushable, like that plastic object. Doesn't have to really think about it. Reaches out and grasps, and the thing automatically stops when he reaches the right grip force. By the way, this is Vikram Pandit, who's a USC student and an employee now at SynTouch. And this is a prosthetic hand, or a version of a prosthetic hands that he used from birth. He was actually an amputee from damage in the womb. So he's a very sophisticated user, and he found it took no time at all to use this hand with this reflex and this tactile sensing because it really is like a hand should be. His brain expects a hand to have these reflexes built into the spinal cord because that's what the brain sees. The brain doesn't see the muscles that are in your hand. It sees all of this intervening control circuitry. And if we get that right, even a very crude approximation of it, suddenly the thing becomes easier to use. And that means that we can start applying similar and more sophisticated types of control and reflexes to tactile sensors that are input on industrial robots so that they can do the kinds of things that industrial robots typically do not do well, like respond to perturbations in a compliant way, or handle something that could easily be jammed, like twisting in a light bulb, where you have to sort of go with the flow and sense how much torque is being applied and make sure that you are actually accomplishing the task rather than just slavishly trying to follow a trajectory, which is what industrial robots typically do. Now, so that's pretty much all I'm going to say about robots as you expect them. Now I'm going to talk about a very different kind of robot that we've been working on for the last few years, which is probably of more interest to you. And that is a robot that can judge the feel of materials. When we first came up with the sensor, Jeremy Fischel, who's now director of research at SynTouch, was doing his doctoral thesis, and he wanted to show how good the sensor was. So we had this problem that we posed of identifying textured materials. So we got 117 different textured materials, and sort of one of everything you can buy in a hardware store, in a fabric store, in a stationery store. We drove clerks nuts. And we said, okay, if we're so good at exploring these and collecting information about how they feel, can we identify them? So we trained up the system. It made stroking movements of various sorts. I won't get into all the technical details. Collected a database of experience on what these materials felt like. And then we said, okay, robot, which one is this out of 117? And lo and behold, 95% of the time, it got it dead on. And it took only about 5 exploratory movements to say, this is what it is. And when it made mistakes, it would confuse two things that humans couldn't tell apart at all. If you showed humans those two samples and said, this is A, this is B, now which one is it? They were completely confused. In fact, we could separate things that humans couldn't tell apart with this robot. And we've recently extended this now to a database of 500 materials and more dimensions, where we're not looking just at texture, but at hardness and thermal properties and all those other things that the sensor can do. So what does that mean? Well, it means that we're now in a position to objectively quantify how stuff feels. After we published this paper about the 117 materials, we were amazed. We started getting calls from people like Procter & Gamble, L'Oreal, Ford Motor Company. What do they have in common? They all sell products on the basis of how they feel. I mean, Procter & Gamble sells Charmin toilet paper, right? For the last 30 years, they have sold Charmin toilet paper on the basis of how it feels, right? Don't squeeze the Charmin, all that stuff. They make Charmin in factories all over the world. They're constantly changing their raw materials and processes. How do they know it still feels like Charmin? They have a professional Charmin squeezer. I kid you not, it's not a joke. And what else could they do? And if he has a bad night on Saturday night and comes in on Monday, God knows what he's going to do. Okay? So they've got a problem. And all these other companies have problems. Ford Motor Company wants to put together an automobile, and they got bean counters who want to pick the cheapest possible materials they can put for the dashboard and the seat coverings. But they know that when you sit in the thing, you're going to say, oh, the car looks good, but it feels tinny, I'm out of here. And now they've got 10 million cars they can't sell. This is not good. How do they design it in the first place? Well, they have experts or focus groups. People come in and go, yeah, that feels okay. Or no, that feels tinny. You can't run $1 billion corporation that way. And so what we think we're now on the verge of doing, we're working with about a dozen of these Fortune 500 companies, is coming up with the dimensions of touch. Now, most of you will be familiar with the dimensions of color because there's something called the Pantone standard. About 50 years ago, there was a problem. Pantone is essentially the color palette that you see whenever you go into PowerPoint or any of these design tools. It's the world standard for color, and it was developed because 50 or 60 years ago, if you wanted to get brochures printed twice, one run, the color wouldn't look like the next. If you got injection molded plastics and you had 2 runs of your product and the 2 versions of the product from different runs were sitting side by side on the shelf, they didn't have the same color because there were no standards. So somebody Lawrence Herbert came up with the Pantone color standard, which is now the standard. So we need to do the same thing for touch, and that's what we're doing. This represents the 15 dimensions of touch, slightly more complicated problem than color. And this is one material in the way it works out into the 15 different dimensions. We have dimensions that are related to texture, as I showed you before, dimensions that are related to the frictional properties, dimensions related to compliance. You know, is it like memory foam? Does it deform? Is it hard? Is it bounce? Is it things related to the thermal properties? How quickly does it cool? How consistently? And adhesive tack. You know, does it feel tacky? And so we're in the process. We've actually characterized the 500 materials now in our set. And we think that this is really going to change how designers select products, materials that go into their products, how they quality control things that are actually coming off the assembly line. I think eventually we may see this revolutionize e-commerce, because when you want to buy things like clothing or towels, you can see what color they're going to be on the internet because there's a color standard. You can get a pretty good idea what their sizes are going to be because there are size standards, or even custom programs now that'll measure your exact shape and color, custom fit your clothing to you. Okay? But you don't know how it's going to feel. And so if there was an objective standard where you could say, okay, I've got this piece of clothing that I really like, how close is that to the way this feels? And no, then I think we would see a vast increase in the ways in which people could source materials for their products, or the ways in which people would purchase products that are based now on not just their look, but also their feel. Meanwhile, of course, we're busily putting tactile sensors on anybody's robotic hand and waiting for the industry to develop all the rest of the control algorithms that are necessary so that robots now can use that sense of touch to handle everyday objects and work safely in unstructured work environments. That's going to be a much harder problem than I think a lot of people think. I don't think robots are going to take over our jobs anytime too soon, at least jobs that require the sort of sophisticated judgment that humans uniquely have. But the journey of 1,000 steps, the journey of 1,000 miles starts with a single step, and I think tactile sensing is certainly an essential attribute of any sentient organism or machine. So we think eventually this will be part of the mix. So I'm going to stop there because there's just all kinds of different directions. One of the things we're trying to decide at SynTouch is where do we go? Do we put our emphasis in prosthetic hands, which are kind of rewarding to do for people? Do we put it in industrial robots, which are going to evolve in their own ways for many different demands that are external to us, or in this brave new world of objectively measuring and specifying products? And I'll take any questions, and like I said, if people want to come up here afterwards and play with that, I've got the live demo working here. Thank you.